So greetings, let's move on with the so-called randomized online algorithms. Randomized online algorithms. So basically randomized means that, well, it's not definite for a given input what you will respond, but you can use some sort of a random number generator. So basically formally, so if we have an input, the sigma, say sigma 1, sigma 2, sigma 3, and so on, and we are just dealing with the teeth request, and we already have output some sort of actions for the first part of the input. So it's of course tau and so on, tau t minus 1. Then, and also we have some sort of random number source. Random number generator, or whatever it's you prefer to call. So then an algorithm, just to determine the teeth output, can use the random number source, can use the whole input sequence as well, and it can use the previous answers it gave. And this means that we are very well unrestricted in our responses. Now in this case, since we have a random number source, it might happen that some of the possible outcomes have a smaller cost and some of the possible outcomes have a larger cost. So for these algorithms, we compute an upper bound for something namely, for a given sigma input, we still calculate the optimum cost and just divide something by it. And of course, I'm just running the algorithm on sigma and check the cost of the result. But since it can be possibly smaller, possibly larger, this is just some sort of random variables, so I can compute the expected value of this random stuff. So it's just the expected cost the algorithm pays. So it's just the expected cost of A on sigma. And of course, this fraction, if this fraction is smaller than or equal to some number c for each possible sigma, then we say that the algorithm is C competitive. Now let's just try an example for this, because this is a bit more abstract than it should be. And of course we'll just check the ski rental algorithm. So for example, if in the ski rental problem the price of the ski is, say, 4 as usual. And the algorithm works as follows. So for the first 2 snowy days, we are always renting. Just rent. But on the third one, we are using some random choice. So on the third one, we just flip a coin and we will buy or rent with a 50-50% choice. So it's just 50% for rent and 50% for buy. Now, of course, if we buy the ski on the third day, then we are done. But if not, then on the fourth day, we will definitely buy it. On the fourth snowy day, we will buy the ski. If we didn't do this earlier. Now, what does it mean? So, what's the expected cost of this algorithm? So, how to compute? So, what should I do? The expected cost of the algorithm on sigma divided by the optimum on sigma. Well, usually, again, we are doing some case analysis on the possible inputs. Now I'm writing this in red because it's quite usual to do this, not only for the ski rental problem, of course. So case analysis means that still n is the number of snowy days. And still the optimal cost is always the minimum of the number of snowy days and the price of the ski. So if n is at most 2, then this algorithm will, I'm just checking it back, so for the first 2 snowy days it always runs. Which means that in this case the cost of the algorithm on sigma is definitely 2. So if there is only 1 snowy day, then we pay 1 renting cost, which is the unit cost, so it's 1. And in the case of 2 snowy days, I'm also just spending 2 amounts of money, and the optimum is still n. So in this case, the ratio, and of course, since we have a constant cost, the expected value of this cost is still that constant. So in this case, the expected cost of the algorithm run on sigma divided by the optimum value of sigma is just 1, which means that for these 2 cases, which is collapsed to one single case, this algorithm produces the optimum value. Now, if n is 3, say, so there are 3 snowy days, what can happen? So with 1/2 probability, we will just keep renting on the third day as well. And with 1/2 probability, we will just rent for the first 2 days, and then we will buy the ski. Right? Now here the cost is 3. Here the cost is well, it's 2, it's 4 plus 4, so it's 6. And then the expected value is of course 1/2 times 3 plus 1/2 times 6. So the expected value, well, the cost of the algorithm run on sigma is just, or it's always the probability times the cost, and then the probability times the cost in the other case, and so on. And this is just 4.5, where the optimum cost for this case is 3, because, well, the minimum of n and b, which is 4 in this example, is 3, because 3 is smaller, which means that the ratio is 4.5 divided by 3, which is 1.5. Now that's actually not so bad, because recall that the optimum deterministic algorithm is 2 minus 1 over b competitive, which is 1.75 competitive. So for this case, we are still better than the optimum deterministic algorithm. But we haven't covered all the cases yet. So it's just if n equals 3, 4, let it be just at least 4. Then of course the optimum is 4. Now the algorithm's cost. So we will have 1/2 probability where we just rent and decide to rent on the third day as well. But this particular algorithm says that if there is a fourth day, then we buy, if we didn't do it. So in this algorithm, I will definitely buy in this case. Or with 1/2 probability, I will already buy the skis on the third day, and then I'm just skipping on the fourth day. And of course, if there are more days, because here it's at least 4, so I'm just keep skipping and I'm just keep skipping. Now, what's the cost of this stuff? So the cost is just this, so it's 3 for renting and plus 4, which is 1/2 times 7, plus 1/2 times, now it's only 2 and 4, which is 1/2 times 6. So it's just the algorithm's expected value is just 13 over 2, 6.5 if you wish. And then the ratio is 13 over 2, yeah, this guy here, divided by 4, the optimum value, which is just 13 over 8. Now for these cases, but here we had a ratio of well, it was 14 over 8 for the deterministic one, and here we have what? Here we have that the algorithm's cost in expectations is just the maximum of the value. Oops, that's not the ratio. So I just computed all the possible ratios for all the possible classes of inputs, and I just have to take the maximum of these values in order to get the competitive ratio, because each of these ratios is smaller than or equal to the maximum. So the maximum is, well, 13 over 8 is, well, it's larger than 1/2, because 1/2 is just 12 over 8. I'm pretty sure in that. So it's 13 over 8. I'm just, well, probably I'm able to compute this, but so it's something like 1.6. And this means that this particular algorithm, if the price of the skis is 4, then this particular algorithm's competitive ratio, that's this one, an upper bound for that, is better than that one, which was the optimal choice for the case of deterministic algorithms. Which means that by applying randomization, we are just able to improve the ratio, well, at least in expectations. So it's for each input we are just so there are inputs for which the algorithm's expected value become worse, because for B4 this would be still an optimal case. So for those inputs, having exactly 3 snowy days, the expectation will be 1/2, while for B4, A4, the optimal deterministic algorithm, it was still 1. So the expected value can be worse for some inputs. But in general, the guarantee that for all possible inputs it's better is just an improvement. So for the worst case, it became better, and this is which counts as an improvement in this subject. So let's just do this a bit more parametricized. So we were just doing this for the case of b equals 4 and with a fixed setting of choosing probabilities by 1/2, day 3 and day 4. We are just trying to improve this and generalize this as follows. Analyze the following algorithm. Now b is a parameter and that's not the constant 4. So analyze the following probabilistic algorithm. So now b is not fixed, but we buy the skis on the 3/4 b day, snowy day, of course. This is the same as we've done before, because if b equals 4, then it was day 3 with probability, but in this time the probability won't be 1/2, so it probability let's see, p for some p between 0 and 1, and if we didn't do that, then we buy on the bth snowy day. And okay, so we'll try to compute the expected value of this algorithm, and we will try to optimize this value p. Optimize p to get a good competitive ratio. So okay, how do we solve such an exercise? Because that's an exercise, of course. So I'm just writing here that solution. Again, we are just doing a case analysis. Case analysis, of course, on all the possible inputs. So it doesn't really matter that you have now a parameter b. It doesn't really matter you have a parameter p. You are usually doing a case analysis. So for the first case, the two algorithms behave the same way. So it's essentially two algorithms. One algorithm is say, or just run a 3 over 4 b with a probability of p. We couldn't denote this like this. Remember, a indexed by something meant that we are just renting and renting and renting, and if this index arrives as an index of a snowy day, then we buy the ski. So a1 was buy on the first day, a3 was buy on the third day, and e3 over 4b was buy on the 3 over 4th day. Or you are just running a b with a probability of 1 minus b. It's the same. So it doesn't really matter that you decide only on this day whether to buy or not, or you are deciding in advance, and with a probability of p you are just running this algorithm, and with a probability of 1 minus p you are just running this algorithm. But that's why I'm saying that these two algorithms behave the same way, because if n is smaller than this checkpoint, then this guy is just keep renting and this guy is also just keeping renting. So if n, so the two algorithms behave the same way for those inputs for which n, the number of snowy days, is smaller than 3 or 4 b's. Now in this case the optimum is of course n, because it's always the minimum of n and b, and n is of course smaller than b in this case. And the algorithm's cost is again, because we are just keep renting and renting and renting in both cases, the cost of the algorithm is n, so the ratio is, I think I will just write the ratios in, say, red, n divided by n is 1. Wow. Now then, the second case is when the first algorithm which we chose but probability p will buy the ski, but the second one won't. Now in this case, again, since n is smaller than b, the optimum value is n. For these cases, it's better just to keep renting. Now the algorithm's cost, now what's this? So with a probability of p, I'm running this a3 over 4, right? So it's just the probability of p, I'm just running this algorithm. Now that algorithm will just spend 3 over 4 b minus 1 days to rent, and then it will buy the skis. prematurely in this case, but yeah. But that's the last point where it spends money, because if the algorithm buys the keys, then we won't spend more money. And with probability 1 minus p, we are running the algorithm AB, which, since there are no b snowy days, will just spend n. Just renting for n days. And then I just have to bound this ratio algorithm divided by optimum, which is, in this case, I will just put the terms, I will just try to put the terms here, so it's 7 over 8 b's times b, so it's 7 over 4 p times b, okay, minus b, yeah, that's fine, plus 1 minus p divided by, multiplied by n, and this whole stuff is divided by n. Now I want to make this a number. Now p is just a constant, but for cancelling out the terms, I'll just have to bound this guy here. But since 3 over 4 b's is smaller than or equal to n, I get that b, in this case, is smaller than or equal to 4 over 3 b's. I was just multiplying by 4 over n's, sorry. I was just multiplying. So this means that 7 over 4 b's is a lower bound for, and I'm just okay, so it's 3 times n, which is just 7 over 3 n's, yeah, times p. So this means that this ratio is smaller than or equal to 7 over 3 p's times n plus 1 minus p times n minus p divided by n. Now these two things together are n times, so we have 1 n's and another 7 over 3 n's, which is 10 over 3 p, no, not exactly, okay, so we have 1 n, okay, minus p plus 7 over 6, so it's 1 n plus 4 over 3 p minus p. Well, we just eradicate this guy here, so since p is positive, or at least non-negative, we can just get rid of it and just cancel out those n's, and we will get 1 plus 4 over 3 times p. So this is a ratio, an upper bound for the ratio. Now in this case it contains a p, which is not that bad actually. I'm just drawing a line here because that's a different exercise. But yet we will have to solve the problem for the third case as well. Hopefully it will be easier, small a bit. So the last case is where b is lower bound for n, because in this case both algorithms will buy the keys eventually, and also the optimum value will be b. So in this case, the optimum value is b, and the algorithm's cost in this case is okay. So with the probability of p, I'm running the algorithm which buys the ski on this checkpoint, on the first checkpoint. That's -1, that's plus b. And then with the probability of 1 minus p, I'm just running the other algorithm which runs for b minus 1 days, and then it buys the ski. And now I will have to compute the ratio of these two things, or at least give an upper bound for that. So algorithm divided by opt is, in this case, I'm just trying to collect all these terms again. So it's again 7/4 b's minus 1 times p, okay. So it's 7/4 b's. I will collect the terms, I will later collect the terms, times p minus p. Okay, now here we have 2 b's. So it's plus 1 minus p. I think it's better to expand. So it's 2 b's minus p times 2 b's, okay, minus, so it's plus p minus 1, right, from this part, divided by b. Okay, so we have to compute an upper bound for this guy. So of course the minus p and the plus p just cancels out, and if I'm just saying that I have to give you an upper bound, then I don't have to deal with the -1 there. And then if I'm just cancelling out these b's from all the terms, I will get 2. So that's -2 b's, and this is plus 7/4 b's, and of course since 2 is 8/4, this is minus p divided by 4, and that's an upper bound for this ratio. So that's the third one. So this means that the ratio, and of course this means that the ratio of this algorithm is, again, I have to collect these for the ratios for all the cases and take the maximum of them. So in this case I should collect the 1, I should collect the 1 plus 4/3, and I should collect the 2 minus p/4, and let's just take the max of these guys. Now of course this guy here, 1 plus 4/3p, is larger than 1, so I don't have to take the 1 into account, and the ratio is the maximum of 1 plus 4/3p and 2 minus p/4, say. We could have given a more precise bound if we haven't cancelled out this -1 here. And in that case we would also have this -1/b if you want to keep this a bit more precise, but we won't do that in that case. But if you wish, you can just recompute the optimum for that setting. Now this is the competitive ratio in general. So, and we just have to bound this guy somehow, because that was the second exercise. So optimize P to get a good competitive ratio. I'm not saying that the best possible, because we are not computing everything exactly. So here we just get rid of the -1, here we just get rid of the -1 somewhere as well, or the minus P, yeah, minus P divided by N, yeah. So it's not an exact computation, but how can we minimize this guy? So the question is, if I have this competitive ratio, how can I set P, how can I choose a value for P in order to minimize this term? Now, if there is only one variable, then it's fairly easy to do this, because I'm just drawing these functions. So here is P, right? Here is the 0, P equals 0, and here is the P equals 1. And then we have this 1 plus 4/3 P's. Now, if this is the 1, then at 1 it will take the value of okay, so that's the 2, and it will be slightly above 2. So this line here is the 1 plus 4/3p. And for the 2 minus p over 4, it will be something like this. It's just below 2, that p equals 1. But of course, these two things are both lines, so they are just straight lines. Okay then, and the maximum of these two lines is this guy here. The maximum of these two guys. Yeah. And then I have to minimize this red line, and the minimum value is taken here. So the minimum is where 2 minus p over 4 is the same as 1 plus 4/3p. Of course, I first checked whether these two lines meet within 0 and 1 and so on in order to get a probability, but for this 1 equals, I'm just adding p4, so it's p times 1/4 plus 4/3, which is p times, well, it's something divided by 12, so it's 3 plus 16, it's 19 divided by 12, which means that this function is optimized if p is 12/19. In which case, the ratio, the competitive ratio of the algorithm will become, say, so it's this guy here. This is the ratio, the optimum ratio, which is just the value of, say, 1 plus 4/3 times the optimum value of p is 12/19, which is just 1 plus 16/19, so that's 19 plus 16/19, which is 35/19. So this is something a bit smaller, so it's just 2 minus 3/19, if you prefer this. So if b is large enough, this is definitely better than the optimal deterministic algorithm. And if we make an exact computation, not getting rid of this -1, then we will get the maximum, we will get this 1 plus 4/3p equals 2 minus p over 4 minus 1/b, right? So if I'm just keeping this term here, then I'm just having this in my equations, and still the two lines meet in a good place because it's just 1 minus 1 over b. Oops. Should equal again b divided by 4 plus 4 over 3 times b, which is still something like 19 over 12 p's. But in this case, the optimum value for b is just a thing depending on b. Well, it's not that surprising. It's not that surprising. So for this case, if we make a more exact computation, then the optimum value for b is just 12 over 19 times 1 minus 1 over b. And for this case, we are just able to compute the maximum as say 2 minus, so the algorithm's competitive ratio is again just say 1 plus 4 over 3 times this p there. Oops. I just got out of space here, so the ratio is just 1 plus 4 over 3 times this p here there. And you can do the computation. This is slightly better than the previous one, and we can do something even more if we also try to bound this guy here, b divided by n's value, but yeah, so it's not that fruitful to do that, but in general this is how you do optimizing randomized algorithms. You just compute the competitive ratio in a parameterized way, and then do case analysis for the possible set of inputs, and then you just take the maximum of all these values you get, and you just want to minimize the values. Now, in a more general sense, of course, here it was quite easy to get such a bound because there were only 2 lines. But in general, if you want to minimize a maximum, then there is a method for that, which uses well, if your functions are linear, then it uses linear algebra. So in generally we don't draw those graphs. Of course, we don't draw graphs. So if in general I have to minimize the maximum of something, and there are several functions, say there is one function and there is another function and so on, and there is an nth function, and I want to minimize the maximum of them, then of course if these are just lines, then I can say plot the f1x, plot the f2x, plot the fnx, and just determine the maximum, and then I just have to determine the minimum of this complicated function. But we can transform it to a set of inequalities. So in general, how we solve this, we just convert it to a single optimization problem. As follows. So we just let t, the new variable, so there are variables coming for the input, and then there is one single new variable t. This will denote the maximum of these functions. And we just write down that the f1 of x is smaller than or equal to t, and then the f2 of x is also smaller than or equal to t, and so on. Of course, each of these functions will get a value which is at most as large as their maximum. And then I have a set of inequalities, and I want to minimize the t. Now this is quite a general approach, but this is the same as solving the minimization of the maximization of these f1x and so on, and fn of x problems. So I'm just maximizing and then I just want to minimize the x for x. Yeah, good. Now, oops. Okay. For this particular case, I'm just zooming out. I had these two functions. So this is just 1 plus 4 over 3p is smaller than or equal to t, and then 2 minus p over 4 is also smaller than or equal to t. And since p is a probability, I have to write down that explicitly that 0 and 1 are bounds for p. If I'm dealing with probabilities, then I also have to include this, of course, and then I have to minimize t. Now this here, in this case, this is a linear program. So this is a linear program, linear optimization. And you have a course on how to solve linear optimization problems, LP systems. So if you just apply the methods you learned on the LP course, then of course you will get still the optimum value is just p equals 12 over 19, and t will be the same as the optimum value. I'm just peeking it, it was just 35 over 19. So instead of drawing these graphs, which is not that computer friendly, so yeah, of course, and you usually are not only dealing with linear functions, but this method in general helps. So if I want to minimize, and usually I want to minimize the ratio and maximize for all the possible inputs. And yeah, for all the possible inputs eventually boils down to some finite number of case analysis, and for each case I'm just telling you some function which depends on the probability I choose or some other parameter of the algorithm, and I have to set the values of the parameters in order to keep the maximum of these guys to be as low as possible, and that will minimize the competitive ratio of my parameterized randomized algorithm. So in this case I will get well, a sort of optimal P if I'm not cancelling away these -1s here and there, but if I'm just really computing the exact ratio at every place, then the value will be actually corresponding to an optimal algorithm. Otherwise it will just be a good enough P. But when I ask for let's optimize P, I'm not asking you to produce the actual optimum value, because it's quite hard to compute in general cases. For those exercises and those questions, this bounds and these two functions will be enough. So it's fine if you just cancel out this -1, for example, just to get a better behaving fraction. Okay. So next time we will try to do the same, so the randomized algorithms stuff for the paging problem. Till then, bye bye.